Okay, and we're live. Welcome everybody to this week's Azure and AI Show. Um, so up first this week we have Precious, and she's going to do some stuff on Azure domain name systems like DNS, and we have VJ then is going to do some stuff from monolithics to event-driven finance. That's kind of real-time accuracy, resilience, and audibility. We do have two other speakers that's supposed to join us as well. Rajesh is going to do a session from data warehouses to Lakehouse. It's the evolution of analytics in the Microsoft fabric. So that could be interesting. Um, we have Anne Shockton as well. His session on comprehensive fault coverage in self-gating architecture. It's test point strategies for advanced SOCs. So they should be joining us shortly. So Precious, over to you there. So if you want to share your screen.
I think I am sharing my screen. Can I stop my sharing?
No, you can leave your one there. I can see it here. I can be able to control it from my side.
Awesome.
So,
thank you. Thank you.
Okay, Precious, I can see your screen. Yep, understanding DNS zones in Azure. Very good.
Okay, thank you everyone, and welcome to Azure and AI Show. So today, my name is Precious. Today we are going to understand Azure DNS Zone. So this presentation is going to represent a comprehensive guide to managing domain name services in Microsoft Azure, from the basic concepts to advanced private DNS configuration. Now, what is a domain name DNS zone? A DNS zone, domain name system, is like a phone book that helps people find business numbers. A DNS zone helps computers find the IP address for your services. When someone types in your website address on a browser, the DNS zone provides the phone number, that's the IP address, to the computer that they need to connect to. For an example, the zone for mybusiness.com might include records for your website, email servers, or your internal apps. What do they offer? Azure DNS Zone can offer central management. When I talk about central management, it is a single unified location to manage all your domain names and their associated records. You wouldn't need to have a scattered configuration across multiple systems. Also, it offers custom naming. It gives flexibility to use custom memorable names instead of long Azure generated ones that are difficult to remember and work with. It also offers public and private support. It gives support to both public-facing services that customers access and internal private services that only employees within an organization can reach. Now, there are services available in Azure DNS Zone. Some of them are public DNS, private DNS, custom. These are just the four I stated, but there are other services you can find in Azure DNS Zone. Now, when we talk of public DNS, it's like a public phone book. Customers use it to reach your website. Anyone on your internet can look up your domain names and find your services with public DNS. And number two, I have the private DNS. It's like the internal company directly. Employees use it to reach internal apps. These names are only visible within your Azure network, keeping them secure within a confided network. Now, there is the custom DNS. You choose your own DNS servers like the Google DNS or the Cloudflare instead of using Azure defaults. This gives you more control over DNS resolution. Also, number 4, the default DNS. Azure automatically provides basic DNS resolution if you don't configure any. It works out of the box with no setup required. It is the default DNS service provided by Azure that automatically resolves your domain name if you don't configure anything. But for the sake of this presentation and my demonstration, I would further show, I'm going to talk about private DNS zone. It's where I want to specify my presentation towards. So a private DNS zone are essential to keep your internal application hidden from the internet while providing employees with easy to remember names instead of complex IP addresses. So this private DNS zone is for private connectivity, resolution and registration within a private zone in Azure. So it is easy to remember names when you use this DNS zone instead of IP address. This is one of the features it offers. Instead of using long IP address numbers, you can use a simple names like finance.mycorp.corp. So these names are only visible inside the company's Azure network, so they stay secure and hidden from the public internet. Now, what are the key features of private DNS zone? It offers custom domain name. It creates meaningful descriptive name, like I mentioned earlier, the myprivate.corp.mycorp for your internal application that makes sense to your team and businesses. It also offers split horizon DNS. The same DNS can resolve differently inside versus outside the network. For example, a web app.company.com might point to different servers depending on who is looking it up. The request might come from internal or external source. Now, it also offers auto registration. Virtual machines automatically register themselves in the DNS zone when they are created, eliminating manual configuration work. And also, it offers cross-network resolution. This works seamlessly across linked virtual network, allowing services in different networks to find each other easily. Here in my next slide, I have private DNS resiliency. This it's in Azure stores private DNS zone as global resource. Private DNS resilience, one of the features of private DNS resiliency is that Azure stores it as a global resource. It has high availability. If one network fails, DNS remains available for other locations, ensuring continuous services. Also offers multi-region support. Example, if your Europe office network goes down, employees in the US can still resolve names. Now, these are the benefits of private DNS zone. It simplifies setups, complete record support. All the records that a DNS zone offers is also available in private DNS zone. You have the A record that maps hostname to IPv4, and you have the A record that maps hostname to IPv6. You have the canonical name, which is the C name, which and the MX and the rest of them. Now, the network integration, it simplifies hostname resolution between different networks and virtual machines. The last here, which is also not the least, it uses familiar Azure tools, including the portal, the PowerShell, and the CLI for management. So these are the benefits you can find around private DNS in Azure private domain name system. Now, these are the capabilities and the best practices for using private domain name system. Automatic VM registration. Virtual machines automatically register themselves with their private IP addresses when created in Azure. It also enables forward resolution. It also enables reverse lookups, where hostnames from IP address, which is useful for troubleshooting and logging purposes, and also cross-network support works even without pairing configuration. True pairing helps with actual traffic routing between networks. Important notes to consider when creating private DNS zone in Azure. A virtual machine can only link to one private zone if auto registration is enabled. Reverse DNS only works for private IP addresses, not public ones. Avoid using local domains. They don't work. They are not supported in all the operating systems you can find in Azure. Then you have the conditional forwarding is supported via Azure DNS private resolver, which connects Azure with the on-premises network. Now, with this comprehensive explanation around private DNS zone, I am going to head over to my Azure portal to show a demonstration on private DNS zone. Okay. So in my demo here, I have already created a private DNS zone here. So this is my private DNS zone. I have done all the necessary configurations. I'm just going to explain what each and every one of it means. So after creating this private DNS, I named it private.contoso.com. I linked a virtual network to it. So I created this virtual network to link to that private DNS zone. This is my virtual network. I linked this virtual network to that DNS zone and I deployed a virtual machine. So after deploying the virtual machine, before deploying the virtual machine, I enabled auto registration within the virtual network. This is where I linked my virtual network. I linked my virtual network to the DNS, to the private DNS. This is it here. It is enabled. Then, first of all, I did a manual configuration of my VM before enabling the auto registration. So this is my manual setup here. This is a manual setup of my VM. I'm going to, once I turn on my virtual machine, the auto registration will take place. Then when I go back to the record sec, you would see the VM record that's in the DNS zone. But there is one way I confirm this. So one way I confirm this is to come over here to this run command. And I run this PowerShell command. So and what I did, I pinged this my virtual net, the domain name of my virtual machine. I pinged it. Just quickly do it. Ping my Let me confirm the name of my DNS. private.contoso.com. So I'm going to go ahead and ping my VM. My VM. While that is running, I want to go back and confirm my auto registration. So I'm trying to open this portal in another tab. So that way I would view my auto registered virtual machine on the private.contoso.com records set. So yeah, that is it. So the reason we didn't see it earlier was because the virtual machine was turned off. But as much as the virtual machine is running, the server is running, the auto registration would continuously take place because it's being configured. This is what I'm talking about. And you can see auto registration through, but this is a manual setup of a DNS record I set up. So I'm going to want to confirm this. Ping request could not found host. I hope I typed it correctly. You can still see my screen, right?
Yeah, we can still see it, yeah.
Ping. Maybe. It's going to take a little while to populate. So let's give it a little time. Okay, here. Yes. So this is it. When you have a successful DNS registration and resolution, this is one way to confirm it and to ensure that the name server resolves correctly to the DNS. So thank you, and that is it for domain name system today. Okay.
Thank you, Precious, and it was grand. It worked. Anybody, any questions for Precious on DNS? No, we're good. Okay, so Anchok, how are you? Can you hear us?
Yeah, I can hear. Thank you so much.
I think you were having a little trouble there earlier on trying to join us.
Yeah, sorry for that.
Are you okay to share your screen as you're up next?
Yes.
So if you hit the button in the middle of the screen there with the plus,
Okay.
and then you'll see another thing, and it'll say share screen, and then click on entire screen, and I'll see it on my end.
Okay.
Okay. Yeah, there we go. So we can see your screen there now.
Okay. Thank you so much. So myself, Ashok Nandigam, I work at Samsung as a senior staff engineer in Austin, Texas. So today I'm going to present uh, regarding like a self-gating architecture, uh, which talks about how we are reducing power using self-gating architecture and the challenges we have with the clock gating structures. So this is very different from what we are discussing before. This is on the hardware side, where as we are moving towards AI applications, where we have like a GPU and CPU being used a lot. So power has been a big factor for us to make sure that the systems work continuously without any issues. So for that, like in the design, we have to have a clock getting structures which will get the clock for the logic which is not active. So the different ways of getting the clocks are something which are used, like to run the digital logic at a specific frequency. um, the self-gating architecture is a specific architecture where, like when there is no activity on a specific data path, the clock also to that logic is off. um, which that way, like the power impact will be reduced drastically, and we can run multiple GPUs at the same time. But having said that, using that kind of a clock architecture, there is issue with respect to testing, right? What happens is, like after we tape out a chip, like after we produce a chip, like it has to be tested to make sure that it doesn't fail on at the customer site. For that, like when we do the testing, we figured out that like with respect to this self-gating clock structures, there is a challenge in testing the enable part of the clock gating cell, because these are self-gating structures where the logic which is connected to the gate itself is controlling the enable of the clock gating cell. So because of that, like when we are trying to have a different values on the enable, it is not possible to have that, because the clock gating cell itself is controlled by the logic which it is driving. So in this article, I'm going to present like how we are addressing that issue and what is needed for that. um, so in this slide, like I already mentioned that the power challenges we have, especially with the GPUs and the AI applications and the mobile applications. As we keep on increasing, the challenges with the power consumption is quite high. um, and we have to ensure that the products like the GPUs are quite good with respect to not having fault defects, right, on the clock hitting cells. So I'm going to talk about the challenges for the future slides, for the slides. um, this slide talks about the self-gating architecture itself, like how granularity it gives compared to the normal clock gating cells, which I already talked about it. Um, this slide talks about the challenges we have because of the clock getting enabled. is not controlled is controlled by the logic itself. Because of that, the tools are not able to detect the patterns, detect the faults on the clock getting cells, because it is a self-gating cell. um, right. Um, so this slide also talks about the same thing, like how we test the chip is like using the scan patterns, where we keep all the flops in the design into a specific chain, and then we drive the values what we want to test in the design, for example GPU, and get the response from the GPU and see that there are any defects in the particular um, design. So with respect to clock gating cells, since they are gated by the logic which it is driving, right? So it is quite difficult for us to get the coverage on those cells. So the proposed methodology here is to add a test point flop on the enable pin. I mean, instead of um, having the logic which is driven by the self gating itself, which is difficult for us to toggle to change. So we add another flop to the enable pin of the self gating clock gating cell, which will be controlled by the tool. So that way we can test the particular clock gating cell um, during production testing, right? So the whole point here is to add one more flop which will help in testing that particular clock gating cell, and then that particular flop is a part of the scan chain, and then we can drive during the actual testing. So first thing is we have to have a self-gating cell here, and then the second step is like to add a test point in test point, which is nothing but the observation flop here to test the clock gating cell. And then there are different techniques like launch on extra shift, which we call in the ATPG, which has better control to test the particular defect in the clock gating logic. And then that will help in be able to cover the functional gating constraints. So this slide talks about in more details about what a self-gating cell looks like what it is like. It is mainly to get the functional operation of the logic, which is controlled by the clock gating cell, right? So what happens is, like in the design, we'll have a clock propagating all over the design, and then if you don't have clock gating cells, then the entire logic will be in active state when the power domain is unable. So that will impact, I mean, that will have a huge impact on the power. So in order to have a control on the power, so we will have the clock gating cells on the clock path, which will control the clocks based on the functional needs. So the enable pin of the functional clock gating cells will be controlled by the registers, which are programmable. I mean, during the functional scenario, we can program it through the functional test cases, and then it can control the power of the specific CPU based on the requirement. So self-gating cell is a more better gating cell, where it will directly and disable the clock based on the transactions on the data path. So usually data path and the clock paths are different in the design, because the clock paths are used to to propagate all the clocks over the design, and then based on the clocks the data are being captured. But these particular clock gating cells are like we have a dependency of the clock being propagated based on the data. So if there is no transaction on the data, then there is no clock being propagated into the design. That way, like um, even there will be less interaction of the CPU to the GPU in order to reduce the power. So automatically the tool automatically by design, the clocks are propagated based on the data transactions. So this slide talks about the strategies of test point insertion, how we are going to insert the flop. So first thing is we need to identify which part of the design needs a self-gating cell. Not all uh, the GPU needs a self-gating cell, because if we are adding a self-gating cell, clock gating cell, it also comes up with a impact on the area, right? Because it has an extra logic which will to get off the clock based on the data, right? So based on the function, based on the architecture, we have to take a decision on that. And then once the clock gating cells are inserted, then we add a test point, and then those is nothing but a flop, which will control the enable pin of the clock gating cell, and then those flops are connected as part of scan. So scan chains. So scan chains are used to load. I mean, scan chains are nothing but the functional flops itself are stitched in a single chain, and these chains can be controlled during testing. So that way we will get a control on the enable pin of the clock gating cell, and we can validate them using coverage. It's the same thing. I mean, this slide talks about like how the fault coverage functional fault active path is covered. So here, if you see, right, as I explained, the enable pin of the self-gating cell uh, um, has to have expected behavior. So that is what we are going to test. So the enable pin of the functional of the clock gating cell is controlled through a test point, along with the functional logic. So that way we can avoid the dependency of the functional values. Instead of that, we can use the test points, and then be able to test the behavior of the clock gating cell before we ship to the customers. So this explains like transition delay testing, which is like at speed testing, testing at the functional clock frequency. Let's say a GPU is designed for a specific frequency, let's say like 1 gigahertz. So we can also test these paths at that particular frequencies, to see that on the real scenario at a different voltage domain at PVT corners, right? So these gates are really working, and then they are like not having at speed delays defects. Not only stuck at, it's even the at speed high at the higher frequencies also they are able to work or not. So launch on extra shift integration is a specific technique which will help us to have a better control in testing at a high speed at the functional frequencies, based on the GPU, right? So GPUs which are going into mobile have a different frequencies, and which are going into the data center have a different frequency. So based on that, we can test, and using specific test point flops, we can test at that speed. So dedicated test scan enables, these are like the test points which I mentioned. These are actually overhead to the design, because it's an extra flop, right? So we have to be very careful in adding them, right? So instead of having adding each test point for each clock gating cell, we can have a single test point for multiple clock gating cells, and then like control them during pattern generation, which is nothing but ATPG tool does that. So we can use the tool to control them. So so this we have implemented, and then we see that the coverage is nothing but the whether we are able to find out the defects on the particular clock getting cell, right? So on various nodes of the clock getting cells, we are able to toggle like different values like zeros and ones, and then at speed, at a frequency which we are expected to work, the GPU has expected to work. So we can test them. So those are like a base coverage. So after we add the test points, we saw that the coverage has improved, and we are able to find the defects on the clock getting cells, right? So that way, like it has improved the coverage, and then but that has impact on the number of patterns. Patterns is nothing but the number of um, uh, ways of testing, right? We while the chip is in the production, so that will the patterns have increased because we have new test points, so which we need to load, so that will impact the patterns, but that comes with like be able to test this logic, which is very important, so that we don't get the customer returns. So overall, like with the AI accelerators and GPUs, every defect we find before we ship to the customers is very important. The I mean, it has a lot of importance now, like because the life cycle of the chips are needed to be for a longer time, and then as we are using more GPUs to be interconnected, we have to make sure that the chips doesn't are credible, and then they are reliable at a different PVT conditions. So these clock gating cells are really helpful in reducing the power requirement. And then this test points will help in identifying the defects before we ship to the customers, and gives a better confidence on the customer side. From this slides, from this article, what takeaways is like design phase, we have to ensure that we are adding self-gating cells, and then once we decide the self-gating cells, we have to add the test points to control them and to be able to test them, and then use different types of techniques in the ATPG, like LOS pattern generation, to reduce the patterns and be able to test these clock gating cells and the other logic around the clocks, right? And then validate them in the patterns in the mass production and before it goes to the customer side. I think I have done with my slides. Any questions? I can answer.
There's none coming in from the comment section anyway. But I have one question for you. Do you know, when you increase the acceleration in the GPU, will that reduce the lifetime of the GPU?
I mean, when we design the GPUs, so there is a specific frequency we design that. If you are intended to run more than that frequency, it depends. I mean, it could run at a higher frequency based on the design. But then, like it is not just the frequency itself, the speed at which we are running. It also depends upon the technology, what it goes into, like how stable the technology is, like for example 2 nanometer, 3 nanometer, right? So it all depends upon how stable the technology is.
Sure, that's great. VJ, any questions?
No, I'm good. Thanks, Ashok.
Yeah,
Okay,
thank you.
Thanks a million. So I'll put yours, VJ, I'll put yours up on the screen there now. There you go. We can see your screen there now, from monolithics to event-driven finance, real-time accuracy, resilience, and audibility. There you go.
Sounds good. Thank you so much, Frank. Yeah, my name is Vijay Kishore Kumar Jotengia. Today I'm going to share lessons from modernizing large-scale financials systems, specifically how we move from tightly coupled monolith architecture to the federated event-driven finance platform, and which that deliver real-time accuracy, resilience, and adaptability. This presentation is grounded in real-world production experience within regulated financial environment. We'll explore not just architectural theory, but measurable operation impacts. With that, let me move to the another slide. Now, if you look at this another site, which is specifically talking about what are the different monolith challenges. But let's begin with the monolith challenges in a nutshell with respect to traditional financial platform. We're built as a single deployable units, which is kind of traditional, very gigantic artifacts, which include UI, business logic, and data access layer very tightly coupled. At small scale, this works perfectly fine whenever the small scale, smallest banks, if I put that way, that works perfectly fine. But if we talk about a larger bank, investment bank, take example, Bank of America, JPMC, or Wells Fargo, etc. Uh, but as transaction volume grows and regulatory demand increases, monolith reveals structural weaknesses. Independent scaling becomes impossible. Synchronous processing introduces latency bottlenecks, and most critically, event visibility become very limited. You can see that current state of transactions, right? But reconstructing how it reached that state become extremely difficult. In regulated financial systems, that lack of traceability becomes serious operational risk because you talk to so many different systems, which include payment, account. In account as well, take example, account has a uh, checking account, saving account, mortgage account, lending accounts. Those are different kind of account. They talk to this risk talk to different payment processor. So it becomes very fragmented solution. Now, with that, let me move to slide number 3. Here, I'm going to talk more on federated event-driven architecture. Now, to address this limitation, if we shift to federated event-driven architecture, instead of services calling each other synchronously through API, could be REST API and somewhere some socket connection and all, services publish immutable domain event to distributed log. Other services consume those events asynchronously. This introduced three major advantages. The first most important is decoupled services. Each domain can deploy and scale independently. So now, if you want to have a payment system to go first, but you're not waiting on accounts and system to release those changes, on the same time, a processor can go in isolation. The second, which is unified data model, now even become the single source of truth. Rather than at so many different places, they are running their own businesses. They will hold on that one, and now your events become your single source of truth. The third one, asynchronous orchestration, which is very important. In my previous slide, I talked about people work in isolation. In that way, it creates lots of issue with the traceability. Now, with asynchronous orchestration, workload no longer block each other, enabling natural elastically. So if I want to go to production to serve the purpose with respect to changes into some policy related to account opening, I can go in isolation rather than waiting for my core system or downstream system to update something. This transition fundamentally changes how financial system evolves at scale. Right now, definitely this all runs on architecture principle. Let me walk you through with core architecture principle. There are many, but let's just focus on first three, which I just call it out here. There are three core architecture principles that makes this model viable in financial world. First, domain driven design. Event must reflect business meaning, not technical implementation only. For example, payment captured rather than database row update. I don't want to go so much on day-to-day activities, but domain should speak their languages. So that's what take example payment captured rather than you are going on some kind of tuple within the records. Second, independent messaging, which include distributed system provided at least once a delivery. Finance require exactly once impact. Every event handler must safely handle retries without causing duplicate transactions. The third, which is automated observability. Here, event lineage, process timing, and failure models must be captured automatically rather than we have to do more manual interventions. Without a deep visibility, financial system cannot be trusted. So that is core part of that architecture principles. If I move ahead, where I'm going to talk about more on how event streaming infrastructure work. At the center of this architecture sheet, the event streaming is a backbone. I can say that technology like Apache Kafka or Azure Event Hubs provide durable, ordered, and replayable event streams. A producer publishes domain event, consumer process them independently at their own pace. So it's not that you have to be online all the time. So once you are available to face those, this will be available to you. It's like a fire and forget, and someone gonna read it whenever they are available, rather than synchronous messaging. Consumer groups allow horizontal scaling. Date later queue isolate failed events. So there is so many time it happens like lots of your matches is populated and which your receiver don't receive. So we hold them into the system called as a DLQ, which is date later queue. And whenever your system is back to the normal, you can do a revoke call to that system. You can do so many different structure of awakening call within your application, your servers, that all are feasible and you can read it from there. Schema registration enforces contract between producer and consumer. Sometimes I can be a producer, sometimes I can be a consumer, depending on how the domain system works to each other. Most importantly, replay capability allow point-in-time reconstruction and incident recovery without data corruptions. This infrastructure provides both resilience and flexibility on the same time. Schema governance and evolution. This is a core part of any banking system. Does not matter it's a small banking, it's a personal banking or business banking, but these are the core rules. In any distributed system, schema governance is very critical. Even contract must evolve without breaking downstream consumers. Schema registries enforce completely nodes backward, forward, or full. Without governance, event system degrade quickly. Hence, with governance, they scale safely. Uh, this is the part where the pattern for financial accuracy speaks itself. Now we address other part, but let me move to this direction. Now we address one of the most critical element in financial system, preventing duplicate transaction. That's most common problem across the board, but yes, a distributed system guaranteed at least once a delivery. That means event can be retired. To prevent duplicate payments or ledger entries, we implement advocacy patterns. Before processing an event, we check persistent administrative cache. If the key exists, processing stops safely. If not, the event is processed and they can key as a recorded. So there is no duplication will be there. This ensures that retries do not result in duplicate financial impact. In financial platform, this pattern is not optional, it's essential. Let me move to the next part, which is observability. Observability transfer operational reliability. Distributed tracing links every processing step across domain. Each transaction carries correlation ID and trace identifier associated with that one. Real-time metrics monitor latency throughout and error rates. Instead of manually searching logs across the system, engineer can visualize complete transaction flow instantly. This dramatically reduces mean time to resolution during incidents. So whenever we have any instance, we have MTTR, MTTS, we define how long it's going to take to resolve, how long it get to capture. So it reduces very significantly. Audit trails, compliance transparency. One of the strongest advantage of event-driven finance is naturally auditability. Event logs are immutable. They cannot be altered retroactively. This provides a complete transaction history with microsecond level timestamp. Event sourcing enable point-in-time state reconstruction. Compliance report can be generated directly from event metadata itself. For regulated industry, this transparency significantly strengthens audit confidence. In a banking thing, the audit, SOC, SOX compliance, these are the most important part. Without that, even you cannot launch any of your applications. Now, let me move to measurable production outcomes. Architecture must produce measurable outcome. That's very default and expected matrix kind of thing. In production implementation, we observed reduction in payment cycle from 48 hours to under 6 hours. That's kind of conversion. Faster incident resolution enabled by distributed tracing and even lineage visibility. Elastic throughput scaling without monolith bottlenecks, very, very important part as well. Significant reduction in failed message rates through independent handlers and automated retry with exponential backoff. These improves were not theoretical, they are operational excellence or operational results. Reference architecture for ERP modernization. Modernizing legacy ERP systems requires a gradual approach. It's not like a lift and shift going to happen. Rather than rewriting everything, we apply the straggler fig pattern. That's one of the design pattern. Legacy system publish change, data capture event to the streaming backbones. New event-driven service consumes finance data without direct database coupling. Over time, domains are incrementally extracted. This reduces migration risk while maintaining operational continuity. Let me walk you through with the implementation roadmap. A practical implementation roadmap typically include 4 phases, which I call it out: foundation, extract, domain, scale, and governance and resilience. But in foundation, we need to deploy the event streaming platform, establish schema and registry, and implement distributed tracing, so that you can track end-to-end flow in a sequential model or in parallel model as well on the same time. Extract domain, identify bounded context and introduce change data capture from legacy system. When I talk about domain, the definition of domain in finance related to which kind of banking you are in. For example, in personal banking, in business banking, in personal banking, deposit, payment, account, this kind of apple considered as a domain. Phase 3, scaled and governance. Expand federated services and enforce schema governance in policies. Phase 4, resilience. Introduce chaos engineering, automated failure procedures, and enhance observability. Transformation, I believe this is transformation must be deliberate and staged. Let me move to the next slide. Here I'm going to talk few key takeaways. To conclude, there are 3 key takeaways for me. First, architectural decoupling enable independent service evolution while maintaining transactional consistency. Second, operational resilience is achieved through asynchronous processing, independent handler, and automated observability. Third, compliance transparency emerge naturally for immutable event logs and temporal query capabilities. Event-driven finance enable accuracy, resiliency, and auditability at scale. Uh, I think I came to the end. Thank you so much, Frank and team, for this opportunity. For me, architecture is finance is not just about speed; it's about trust at scale. Thank you very much for your time. Over to you, Frank.
Okay, thanks very much. Great presentation. Interesting to know kind of a bit more what's happening behind the scene in banks and things like that. So it's kind of their transition to more modern stuff is very slow, I take it. Yeah.
Exactly. There are lots of reason, right? The audit on same time they need to clearance so many SOX compliance where third-party companies comes in picture and they go through your all audit processes. So it's a lengthy in the process, but now even banking understanding if they want to deliver something to production, it's not gonna work out the traditional orthodox model. They need to move to this event driven model so that they can go in production in isolation rather than going all in one all the time.
And I see it's very strict in as well with the logs. Nobody can interfere with them or delete them or anything like that.
Totally.
Yeah. Any questions, anybody? No, we're good. We're kind of 5 minutes. We have 5 minutes before we end the show. Precious, have you anything else for us?
Not really. I just want to say Vijay and
Ashok.
Ashok. You did a very good job with your presentation, and I kind of learned a lot from you right now.
Thank you so much. I echo the same. Like that was a great presentation on DNS, and Ashok is like a different world for me. I was
Yeah.
always on software, so this gave me some different flavor to learn more from how it works on hardware world. So thank you so much, Ashok and Precious.
Yeah, thank you.
Yeah, we have a kind of a big mix of people coming on here, especially when it's we're talking about Azure and AI. And some weeks we might talk about we might have some agents on and stuff like that. So I'm an MCT as well as a Microsoft MVP, and I'll be giving a talk in the DMCT Summit in Europe in April 21st. And I'm going to be showing educators how to use Copilot and Copilot Studio to teach people with. So, have anybody done anything with any agents yet?
In my world, I started using lots of agents, so yes, I can say that. Nowadays, I started creating agents where I have some monotonous job, so that those will be taken care by agents. Specifically, for example, like every morning we need to go and check lots of logs because this is financial system, so you need to check how transition happened between mainframe system and your existing system. So many messages goes to data later queue, which I talked in today's call. So every need to go manually and cross check, is that impacting any kind of transaction or third party partner payment. We need to do lots of manual thing now with agents, which we are running in every morning is like a CODS job. They are going and reading those messages. They are calling wake up call to the date later queue and doing everything by themselves. So yes, these agents are serving lots of monotonous work into the pattern based mechanism.
Yeah, very good. I actually met the last agent I met there was actually a stock market agent. So
Interesting. That's important.
yeah. So I just kind of got it to pick my favorite site that look up stocks on them, whatever, and just got it to scrape that site for stuff about that company and the future of the of that company and what they predict its share price could be in a year. It's very good because you go onto a website now and just look up a company and you're going to get thousands of pages of everything. These agents now will just break everything down for you. Save you time searching for stuff and everything else like that.
Yeah. I think there's no exception to agents now. Everyone gonna use that one and gonna get rid of even like watching stock. That's sometimes it's very manual. Now agents is generating that data and sending so many alerts on your mobile itself that this is the time because all candles are going in positive or negative direction, buy or versus sell items. So yeah.
Yeah, very good. So we're up on the hour. So thank you everybody for joining us. Another great session. I think Precious, you'll be back again next week with some more stuff on Azure for us. Very good. And we'll have 3 more speakers again next week then. So thank you everybody for joining us and see you again next week.
Yeah. Thank you so much, Frank, and all the best, Precious, for your next session.
Thank you, Frank.
Thank you, guys.
Precious.
Nice.
Thank you, guys. Bye.